Okay, guys, here's what we need to talk about today. Covering combination circuits, here's what's on the IB syllabus that they expect you to know. You should be able to define electromotive force. You should be able to describe the concept of internal resistance, apply the equations for resistors in series and in parallel, draw circuit diagrams, and describe the use of ideal ammeters and voltmeters. So we'll touch on all this today real quickly, and then we'll review for the test. So let's look at EMF, voltage, and internal resistance. EMF, well, first of all, voltage. How would you define voltage? What is a volt? What is potential difference, or potential, for that matter? Ooh. It was on a test. Excellent, excellent. When we talk about voltage, you guys, you should be thinking either work or energy per unit charge. Okay, so voltage is the energy released or the energy used per unit charge. We say a light bulb consumes a certain amount of volts, or there's so much voltage by that resistor. EMF, which stands for electromotive force, is exactly the same thing, except for rather than being used, it's being created. Okay, so in a battery, we say it's a 9-volt battery. The battery generates 9 volts of EMF. Okay, that's the idea. So when we talk about EMF, we're talking about electromotive force, and basically it's the amount of energy created per unit charge, or the amount of work done per unit charge that's created inside of the battery or inside of the generator. So EMF and voltage really are the same thing. We just use the word voltage when it's used and EMF when it's created. Okay? Hayden. The other concept that IB would like you to know is this concept of internal resistance. And here's the deal. You have a battery. The battery has a chemical composition inside of it that generates a certain amount of EMF. If it's a 9-volt battery, it's generating 9 volts of EMF. But you guys remember from the lab we did 2 days ago, you guys were using 9-volt batteries. How many of you actually got 9 volts in your circuit? Anybody? Yeah. You had 8, which is almost 9, but it ain't 9, right? So where did that 1 volt go? The battery uses some voltage because the battery actually has resistance inside of it. So some of that voltage gets dissipated inside the battery, internally, okay, because of what's known as internal resistance. And here are some equations for it. I want to draw you a little picture of it so you can see it better. But basically, EMF generated by a battery is going to equal the total current times big R, which is the external resistance, plus little r, which is the internal resistance. Okay, so remember let's see, V equals IR, right? Yeah, V equals IR. V equals IR, so here we're just saying the total voltage created, the EMF, is equal to the current times the total resistance, the resistance outside the battery plus the resistance inside the battery.
What's the little r?
The internal resistance. Little r is internal resistance, big R is external resistance. So sometimes you'll hear this thing called terminal voltage, or what we talked about in the lab as being the applied voltage, or the voltage you measure in your circuit, or that you get at the terminals of the battery. That's equal to the EMF created by the battery minus the voltage used internally, which is the current times the internal resistance. So here's a basic circuit. We've got a battery, we've got 2 resistors connected in series, right? We've been doing all sorts of work to figure out the resistance in the circuit and the voltage used and all that stuff. What you need to also understand is that this battery is going to have some, so this will have like resistance A and resistor B, and the equivalent resistance is equal to RA plus RB because these are connected in series. Good so far? The reality is this battery is going to have a little bit of resistance inside of it as well. And actually that resistance will grow as the battery ages. That's why batteries die, because their internal resistance increases. So what you can do is you can think of it as if the battery is really a source of EMF and a resistor, okay, all in one. So really it's like having a third resistor in series, but it's inside the battery instead of outside your circuit. So what happens, since the voltage that any of these resistors uses is equal to current times its resistance, I can find the voltage used here, I can find the voltage used here, I can also find the voltage used internally before it ever gets out to the terminals of the battery. That's why a 9-volt battery or a 10-volt or 12-volt battery rarely actually registers that many volts, because some amount of voltage is used internally.
Doesn't a wire produce this?
The wire does too, but it's pretty negligible if it's a good wire. Now, when you guys, let's think about the lab you did 2 days ago. When you added light bulbs in series to your circuit, what happened to the total resistance of that circuit? So therefore, what happened when it went up? So what happened to the total current? It went down. Do you guys remember what happened to the voltage you measured as you changed the number of bulbs? Did it stay the same? Was it perfectly the same? Not when I looked at most of your sheets. Look at your sheets.
No, it increased. The voltage increased as you took off.
Let's think about this for a second. If you measured carefully, what should have happened is as you added bulbs, the total voltage that you got out of the battery actually went up. So take a look. When you're adding bulbs, the current's going up, right? I'm sorry, no, the current's going down. Just testing you. Okay? Right? So now let's look at the battery itself. It's still creating 9 volts, but it's using some voltage internally. The internal resistance hasn't changed, but there's less current going through the battery. So now the voltage used internally, since this has gotten smaller, the voltage used internally has also gotten smaller, which gives you more terminal voltage, more voltage outside of the battery. Let's talk about combination circuits, circuits that aren't just parallel or aren't just series, but a combination of the two. Sometimes these are called complex circuits, sometimes these are called combination circuits. What do? Well, the first thing you do is you try to simplify that circuit so that you could imagine it being a circuit with one resistor. You try to solve for the equivalent resistance of the circuit, okay? That's your first step in any complex circuit. So if you have parallel sections, you break those down and figure out what they would be equal to. And then you figure out, if they're in series with something else, you figure out what they would be equal to, ultimately trying to get to the point of finding the total resistance of the circuit. That's your first step. If you can do that, you'll be able to do lots of other good stuff. Once you've figured out the equivalent resistance, the next piece of information that will be helpful to you is finding the total current. The total current in the circuit. And you guys might have noticed that really there's not a lot of equations. There's really this equation, V equals IR. And you just have to use the right V and the right I and the right R in the right place to get the right answer. But this is the one you use the most. And then there's the power equation sometimes. But when we're solving for circuitry, this is it. This is the equation. Once you've found the total current, now you can start to figure out how much voltage gets used by each resistor, or how much we call it a voltage drop sometimes, okay? Because V equals IR. That's pretty easy. The voltage drop is just the V, used by each resistor. We say the voltage is dropped or because that much energy has been used by that particular device, okay? Once you've found the voltages used at each resistor, you can then do the final step, which is finding how much current flows in each path if you have more than one path. If you have a parallel section, you can then solve for how much current goes through that section. Because remember, if it's in series, if it's just one path, that's equal to the total current, which we've already figured out anyway. So let's look at one. And I know you guys have done a bunch on the homework, so you're already experts. But here's a new one, okay? This is a complex circuit or a combination circuit, okay? Your goal, and this is not a quiz, so you can talk to each other, you can talk to me if you need to. Your goal is to find the reading on ammeter 1, ammeter 2, and ammeter 3, and on voltmeter 1, voltmeter 2, and voltmeter 3. Okay? Assume these are ideal ammeters and voltmeters. Yeah. Okay. All right, let's talk about this then. Some of you finished, some of you still confused, but let's talk about it. Where do we start? We want to find the total resistance, the equivalent resistance. And where do we start doing that? Let's start with the parallels. Great. So what do you get for this section here? This has an equivalent resistance of 5 ohms. And then how about this one down here? Everybody good on that part so far? Any problems? Great. Then how do you find the total resistance of the circuit? You add them all up. You got a 10, a 5, a 6, and a 24, all in series. So what's the total resistance? Everybody good with that? Okay, and then what do we do? Find total current. V over R, 90 over 45, so we get 2 amps, correct? Great. Great. Okay. So now we're cruising along here. So what is ammeter number 3 going to read? What's this going to read? This one says 2 amps. What if I place an ammeter right here? What do we read? 2 amps. And over here? Excellent. You guys are good. Okay. So then let's look at voltmeter number 1. How do we do that? V equals IR. So what do you get? So we get 20 volts there? Yeah? Great. How about V2 over here? Same thing, and you get 12 volts. No problem so far? All right, now it gets trickier with all this other stuff. Let's look at voltmeter number 3. There's a variety of ways to do this. One, you could figure out how the current splits first. But let's do it another way. We'll look at 3 different ways. Let me show you a first way. Let me backtrack for a second. When resistors are in parallel, what is true about the voltage that the resistors use? Same through each branch. They all use the same voltage, okay? So I have 2 amps flowing into this section that is just like a 24 ohm resistor, right? So how many volts would a 24 ohm resistor use? 48. So this reads 48 volts. And if I was to put one here, it would also read 48 volts. They both get 48 volts. Okay? If you take the total current times the total resistance of that section, that will tell you the voltage drop there. Okay? There's other ways to do it, and I'll just briefly gloss over those. Another way to do it would be this. If I knew the current through each path, and I multiplied that current by the resistor in that path, I would get the same answer. But I don't yet know the current through each path. But if I did, I could, right? That's how we're going to find this current. This current is equal to V over R, right? Which we just found V is 48. R is 60. So what do I get? Which is what? 0.8 amps. Now, if I wanted to find the current in this path here, right, I would do the same thing. I would do 48 volts over 40 ohms, and what do I get? 1.2 amps, and that's good because 1.2 and 0.8 should add up to my total current, right? Okay? All right. So Skylar brings up a good point. If I want to find this ammeter, isn't it possible for me just to take the total current, which is 2 amps, and divide it by the number of paths? And in this case, the answer is yes. Why is it in this case? Because they are the same. You can only do that if the resistors are equal. If the resistors are equal, you know the current will be divided up equally. But in this bottom section, it's not equal, so you have to do a little bit harder math. But here I can just do 2/3. But let's go the other way just for fun and see what happens. We know that this is 5 volts, right? So if I wanted to find the current through this path, I equals V over R. I'm sorry, 5 ohms, 10 volts. Thank you. So this section uses 10 volts, right? So if I did 10 volts over 15 ohms in this path, I would get 2/3 also. I get the same answer. We hadn't done it yet, but this whole thing is like a 5 ohm resistor, and the total current is 2 amps, so that would be 10 volts. Okay? What? Such a good question. Okay, here we go. If I measured the potential right there, it'd be 90 volts. If I measured the potential right there, it would be 70 volts. The potential difference from here to here is 20 volts. Okay? So when I say 10 volts, I'm saying the potential difference from here to here is 10 volts. But it would go from 70 down to 60. Yeah? Okay. The last thing I want you to see while we're talking about voltage, let's look at this. 20 volts here plus 10 volts. I've used 30 so far, right? Plus 12, that gets me up to 42, right? Plus 48 gives me what? Yay! Because that's how many we started with. Okay? That's a good way to kind of check that everything's working out for you.
And so when to do current?
Okay, we've talked about this over and over and over, but I'm going to talk about it again to make sure you know it. So here you go. We measure an ammeter. In order to do it, we connect an ammeter in series. And in order for an ammeter to therefore function, so an ammeter has to be connected in series, and in order for an ammeter to work correctly, an ideal ammeter must have 0 resistance, ideally. A Exactly. The voltmeter is opposite. You connect a voltmeter in parallel around the object that you're trying to measure, or so that you can measure the difference in potential between two locations, what we call voltage or potential difference. And a voltmeter, in order to work properly, must have infinite resistance or extremely high resistance. Luke.
How do they get it to be?
If you don't like words, we have pictures. There's a picture. Okay? Look at that. Okay? Voltmeter, ammeter. Here's a schematic of it. Remember, voltmeter in parallel, ammeter in series. You guys hopefully have that down by now, because that's like easy IB points. They'll say, which one is correct? They'll show you a picture. Which one shows the correct connection of a voltmeter and ammeter? And if you can just pick the right one, awesome. Okay, good. All right, let's talk about home circuit breakers, fuses, and electrocution. Okay, that's what it's all about. This is what it comes down to. We have devised things in the world so that electricity is less dangerous, because ultimately it's kind of dangerous. It can either burn your house down or kill you, or both. So we try to prevent that from happening. And the first device that was designed to help prevent death and destruction is a fuse, okay? And the purpose of a fuse, it's just a thin piece of metal that as the current flows through it, it heats up, right? Remember, any metal that has resistance has some resistance that's going to heat up when there's current flowing through it. So as there's current flowing through it, it heats up. Now, this is a parallel circuit. Notice that I've got these three resistors in parallel. Every time you add something in parallel, what happens to the total resistance and the total current? Excellent. And as more current goes through a wire, it gets hotter. The fuse is designed to melt at a certain point. It's just like a filament light bulb, except for this one's supposed to break when the current gets too high. Because notice as the current's going higher and higher, these wires are getting hotter. Usually in a home, the wires are in the walls, and there's wood and insulation and mice in there. And if it gets hotter, it can catch your house on fire. So the fuse is designed to break the circuit before that happens. Okay? So with a fuse, when it breaks, the circuit's broken. And you actually have to go to the fuse box, which homes don't have these so much anymore, but your cars do. Cars still have fuse boxes. You go to the fuse box, and you find the broken fuse, and you pull it out, and you put in a new one. Okay? Yes. Your car has a fuse box with like 30 fuses in it, and each fuse is set up with a circuit that one of them runs your stereo, and one of them runs your windshield wipers, and one of them's the headlights, and one of them's this, that, and the other. And they all have different ratings on them. Some say have a little 5, some have a 10, some have a 15, and that's telling you the maximum amperage before that fuse will break. Now, what some people do, okay, let's say you have an older car, and you keep blowing a fuse every time you put in your favorite Led Zeppelin CD. Okay, cool, crank it, poof, stereo goes out. Crank it, poof, stereo goes out. So you decide that you're going to take that 15-amp fuse and replace it with a 20-amp fuse.
Yeah, you are.
Why is that a bad idea?
Because then things can heat up.
Okay. Now you're allowing more current through the circuit than that circuit was designed for. It's going to get hot. It's potentially going to melt stuff inside your dashboard, maybe catch your car on fire. Bad news, okay? So when your fuses are breaking, it's because there's something wrong with the circuit that you need to be dealing with, okay? Carson. And so in older homes, they used to have fuse boxes. You go in, there's a big fuse, but now you usually see fuses in cars now. And I have to, okay. So what we do now in most modern homes is we don't use fuses anymore. We use circuit breakers, but the idea is the same. The circuit breaker is there to prevent overheating and burning down of your house. Your house is divided up into multiple circuits, and within each circuit, everything's wired in parallel, right? We know that because when one light bulb goes out, they don't all go out in the living room. But when things are in parallel, every time you turn something on, more current flows through that circuit. A circuit breaker is an ingenious little device that instead of just being a piece of metal that melts, this is really not working, okay, what we do is we take two pieces of metal, we glue them together in a long strip called a bimetallic strip, and here's my circuit, okay? They're different kinds of metal. As current flows through these two pieces of metal, they start to heat up, but since they're different kinds of metal, they heat at different rates, and they actually expand at different rates, because when things heat up, they tend to expand. But different metals will have different rates of expansion. So I've got two pieces of metal globbed together, heating up, and expanding at different rates. What will my bimetallic strip do? It would if it could, but it can't, so it won't, because it's all globbed together, okay? How about that? Okay? So it's stuck together, and it can't come apart. So what will it do instead? No, that'd be bad. Imagine this one on the bottom gets longer than the one on the top. What's it going to do?
It's going to separate the current.
Someone kind of said something. It's going to bend. The strip is going to start to curve. You with me? And as it curves, if it gets hotter and hotter, eventually it'll curve so much that it breaks the circuit. Boom, circuit breaker. It breaks the circuit, no more current flows. Now they've added things to it. This is a very simplistic version. In a true circuit breaker, there's some springs and some levers and some latches so that when it gets too hot, it starts to bend, and then it goes pop, and it flips open, and it stays open. So you have to walk into your garage and open the circuit breaker box and find the one that's flipped the switch and switch it back. And that closes it so that your circuit works again. If you have not turned off any devices, like your hairdryer and your blender and everything, it'll pop it again. So what you do is you turn off some devices, and then you go turn it on, and everything works. That's the way modern circuit breakers work. Let's talk about. Did we talk about this yet? Okay, check this out. You may have noticed in your life that some things you plug in have 3 prongs and some have 2, right? It's kind of like the Sneetches, right? Some have stars on their bellies and some don't, right? And then they go through the machine and get the other ones, and then the other ones. You guys, if you pay attention not to the Sneetches but to the 3-prong plugs, you'll notice that generally an item that has a 3-prong plug is something that has a metallic exterior, like my stereo at home, for example, okay? The third plug is a ground. Yes, the third plug in any outlet, if your house is wired correctly, that third opening in every outlet is just a copper wire that's attached to the earth. It's a very low resistance path to the earth. And the point is this. If your microwave in picture A is working perfectly, everything's good, and you walk up and you pat your microwave by putting your hand on the top, and nothing happens while you're cooking your popcorn. Life's good. But if something happened inside your microwave and a wire broke, and it was dangling around and touching the exterior of the microwave from the inside, you know what I mean? Like there's just a wire hanging there, and you walked up and touched it, you could potentially create a circuit that comes from the 120 volts in the wall through you and into the ground, and you would get electrocuted and probably die. It would be bad. You would die from if you could die from a 120 volt outlet very easily. Yes. And so what this third prong does is it's basically just a ground wire. It's a connection between the casing and the earth, so that if something were to break inside, it would create a path for that electricity to flow very easily, more easily than flowing through you, and it makes it safer. Most devices that don't have some kind of metal casing or whatever, they tend to not have 3-prong plugs, but some do. And yeah. Last thing I want to talk about is this thing called a ground fault interrupter, and I think this is like what you talked about, Todd, you're asking about. So think about your home for a second. In the bathroom, the outlets in your bathroom are usually different than the outlets everywhere else in your house. How are they different? What do you notice? They have the little reset button, okay? And the kitchen will have it too. Sometimes the kitchen will have it too. Excellent. Notice in your bathroom and in the kitchen, you're near water. And water is usually carried in pipes that are also usually metal, but sometimes they're PVC. But anyway, water and metal is dangerous because it conducts electricity really well. So imagine you're sitting there playing in the sink with the bubbly water, and you got it filled with warm water, and you're holding onto it. That water is connected to the ground through pipes, okay? And you reach over and grab your electric razor, which has been, you haven't fixed it, and it's got exposed wires, but you didn't want to go buy a new one, and it's plugged into the wall, and you grab it, and your hand's in the sink. Suddenly, you've made a really fine path for that electricity to travel through to the ground, and you can die very quickly. So what we've done in modern society today is we've developed a thing called a ground fault interrupter, and in those special outlets with the reset buttons, there's a magnet and some wires, and it can sense how much current is flowing. And as soon as the instant there's a spike in current, if the current suddenly goes up for any reason whatsoever, that little thing will pop and break the circuit and save your life. That's the whole goal. So notice those tend to be in places that are located near water. And hair dryers nowadays in America, most hair dryers you buy will have one built into it. It's because for some reason, some people thought it was a good idea to dry their hair in the bathtub, and that's dangerous. Okay, finally, I want you to see this, and I want you to know that you have seen this before. This is a page in your data booklet. So if you have a question on a test that has a circuit and there are some designs on that circuit that you don't recognize, remember this page, okay? There are some things you won't, there's some things you'll see more often than others. I mean, obviously, a battery in a cell you'll see a lot. This is what they use for a lamp. This is what they use for a switch. Obviously, ammeter and voltmeter, we know those, or just a plain old resistor. Transformer we will talk about when we get into alternating current. A potentiometer you should know about, though you may not recognize the word. A potentiometer is a variable resistor, sometimes called a rheostat. But remember we used the variable resistors in that lab where we slid the things? That's this. This thing can slide back and forth. Okay? Those are the main symbols.